Lab 4, Circuits and Capacitors. The purpose of this lab was to use the principles of energy conservation, or the loop rule, and current conservation to A. Predict the behavior of circuits containing resistors in series and parallel. B. Use multimeters to measure the actual values of conventional current and potential differences in the circuit. And C. Examine the behavior of ohmic resistors and capacitors. Some of the physics principles we used in this lab were Ohm's law, or voltage equals current times resistance. Capacitance equals voltage divided by resistance. The node rule, meaning that the current flowing in must equal the current flowing out of a circuit. And 3, the loop rule. The total potential voltage must equal 0 around an entire circuit. We start with a circuit of 2 resistors, and we predicted the current. So we had 2 resistors, and we had an ammeter here and an ammeter here, with a resistor of 47 ohms and 100 ohms. And we predicted that the current across the current at eyes, both eyes, would be 0.02 amps, and the ammeters calculated that it was 0.02 amps. And then we reversed one of the ammeters, and the current was negative 0.02 amps. Open circuit. Here we had an open circuit where we disconnected one of the ammeters with a voltmeter, and the voltage reading read 3 volts. And the ammeter, the one that we kept, the ammeter that we kept, read that there's 0 current. This is because it's an open circuit and that current is not running through. The voltmeter has a large resistance and does not allow current to run through it. Potential differences. So we calculated the potential difference across the battery to be 3 volts, across this wire to be 0, across the 47 ohm resistor to be negative 0.96 volts, across this little short wire to be 0, across the 100 ohm resistor to be negative 2.04 volts, and across the wire ammeter in this wire to be 0 volts. Here's a little graph of how it looks across the entire circuit. And this does follow the loop rule, where 3 volts minus 0.96 minus 2.04 equals 0. Circuit with ammeters in parallel. We placed an ammeter in parallel to the 100 ohm resistor, and the current increased to 0.06 amps. Here the current followed the path of least resistance through the ammeter and not through the 100 ohm resistor, so the current is only affected by the 47 ohm resistor, and we calculated it. Well, you could calculate it, but we also got the reading from the ammeter to be 0.06 amps. Resistance. Ohm's law states that voltage equals current times resistance. With the rearrangement, we can get resistance equals voltage divided by current. And this allows us to calculate resistance at different parts of the circuit. The resistance of the 47 ohm resistor was 0.96 volts divided by 0.02 amps. And we got 48 ohms, which is roughly 47. And on the second one, the 100 ohm, we got 102 ohms, which is very close to 100 ohms. And along the wire and ammeter, 0 ohms. Then we created an RC circuit with a 9 volt battery, 200 millifarad capacitor, 10 ohm bulb, and 20 ohm bulb. During the charging, the bulb was started out very bright, and then it decreased as with time. There's no current when that capacitor was fully charged across the circuit. And then while discharging, the bulb was very bright at first, then it decreased with time, and no current through the capacitor when it was fully discharged. The bulb was off. Current travels in the opposite direction in a capacitor. Here's some of our readings. The time constant of our capacitor was 5 seconds. In conclusion, what if we were doing this lab real life and used an actual ammeter? Well, real ammeters have resistance, a small bit, but they actually do have resistance, as opposed to our lab where we used an electronic version which had 0 resistance, so the readings would all be a little off. And what if we're doing the real lab? Used a real battery to charge the real capacitor with no resistance in the current. In ideal situation, the capacitor would be charged instantaneously, but all components have resistance, so it doesn't quite work that way.